This is Polarized Light Microscopy in Archaeology. And this is Lecture 4, Properties. So, knowing properties of inclusions in thin section is very important. In fact, it's pretty much the entire point of this course, because it enables you to identify inclusions, but even more importantly, it enables you to describe them. Because if it is your destiny to go forth and do petrographic analysis one day, you will be doing it on your own. I will not be following you around. Professor Sunahara will not be following you around identifying that stray mineral that you can't quite identify. You will need to identify it on your own, and if you can't identify it, you will need to describe it. So you will describe the inclusions, you will be able to group fabrics, petrofabrics of pottery based on these descriptions of unknown inclusions, and be successful ceramic petrologists, whether you can identify every single mineral in your thin section or not. So describing based on the properties is far more important than actually identifying things. So, but it's also how do you identify things. So here we have a mineral in a piece of pottery, several minerals actually, but this one's quite interesting. You see, this is plain polarized light, and this is plain polarized light, but the stage has been rotated slightly, so you can see it's changed color. So you might remember that this is called pleochroism. Okay, that it changes as it moves. Another thing you might notice is it has these cracks which are quite straight and parallel, and see, these ones actually are parallel to this one. And also there's another one, it actually shows up here as well, which is at about 180 degrees from these ones, which would suggest this has two cleavages, not 180 degrees, 120 degrees, at 120 degrees. So that should give you a very good idea of which mineral you're looking at here. It's an amphibole, possibly hornblende. So this sheet I will be using to talk about these properties, and as you can see, they can be divided into properties involving cross-polarized light and properties involving plane polarized light. Okay, although some actually are cross-polarized light, but we'll get to that. And these enable you to identify minerals, but there are far more minerals in the world than in this list. In fact, when I originally studied geology, our list of rock-forming minerals we had to study was a lot longer than this. And there are actually more than that on top of that. So it may be that the mineral you have found is not on this list. It may be on this list, but it's not identifying for all sorts of reasons to do with the firing of the pottery and it being very rare in the pottery entirely. So that's why the properties, your ability to describe it, is more important than identifying it. So the first thing we'll be looking at the cross-polar's attributes. And so you have opaque things, you have isotropic things, and anisotropic things. So opaque, we covered a bit, and of course, as I said, we'll be repeating covering the same things as I'm looking at the same things from different angles. So now we're going through the properties. So opaque things are opaque. Isotropic things is light propagated equally in all directions, which could be because it's amorphous, like a glass, including a volcanic glass, or because it's an isometric crystal. And you have anisotropic materials. Light is propagated unequally in different directions, also called birefringence, and so that forms all these psychedelic colors. Also notice these So what are they? Do you think they're opaque? I think they're actually garnets by their shape. So in plain polarized light, they would not. Light would pass through them. So what do we have next? Birefringence. So we have high birefringence, second, third order birefringence, and first order birefringence. Remember I talked about the thing at the bottom. You have like first order birefringence. All of these are actually first order grey. Then you have the colourful things, second, third order birefringence. And you have the way up here birefringence, which we can actually see better in an actual Michel-Levy interference colour chart. So here you can see the first order, second, third order, and the way up here orders. And of course it's important to take reference that this is the actual thickness of a thin section. So this is the range we're looking at. And there's a nice line to emphasize it. So quartz is about here. And so this is first order grey. Biotite is between here and here. So it's all sorts of these nice, quite colourful colours. Whereas calcite is way up here somewhere. 0.154 to 0.174. So if you look 0.1, yeah, see, down here somewhere. It's right below here. So it's going to be like way off. I'm going on my screen, which is bigger than the screen, but it's way off over here somewhere. And so this becomes very pastel-y shades. Really quite insipid, actually. Here we have calcite. This looks like a marble or something, large intergrown crystals of calcite. Here we have cross-polarized light, and here we have plain polarized light. So here it's just a transparent colorless crystal, and here it's got its birefringence. And here you can see this has some colors. It's very pastel, so pastel it's almost white light, whereas this practically is white light. However, it's not. It's actually very high order birefringence. And there is a way of distinguishing the two, which we'll be showing you in the first lab. Phosphates have very low birefringence. This is this is actually a piece of pottery. I think it's actually a piece from Professor Banning's research in the Jordan, because this is pottery, and in it are inclusions of phosphatoids and also bones, actual bones, which of course is the source of phosphatoids. And so this is where it enables you to possibly find something very diagnostic to help you find out what these things are. And you might at first think that they're just holes, or you might think they're isotropic because they are almost isotropic. But you can see there's just a little bit of birefringence there, just a little bit. And so you know that this is very low birefringence and typical phosphate. And in plain polarized light, you can see, oh yeah, this looks like a bone, this looks like a phosphatic ooze. Yeah, that's what's going on here. So, then we have the colors of things. These things just have colors. These things have colors which change. Pleochroism, hornblende, biotite, tourmaline. So these are the polarized light effects. You have absorption, which means it has a color, and pleochroism, which means the absorption is different in different directions of the crystal. And of course you see that in plain polarized light because it's plain polarized light. It's not ordinary light, it's plain polarized light. So at different orientations, as you rotate the stage, the color will change because you're looking at it in different directions. So here is a garnet. So garnet is the most well-known isotropic mineral. And here you can see it's slightly pink. So you compare it to this out here. So this is plain polarized light. And this is in cross-polarized light. You can see you can't see a thing. And so this is an isometric crystal, which is isotropic. and slightly pink because of absorption. So here we have pleochroism of a type of amphibole called glaucophane, which actually looks blue. You see, when it forms a metamorphic rock, they often call it blue schist. And you can see this blueness actually also shows up in the absorption in thin section in plain polarized light. And when you rotate the stage, it can turn from this bluey to this purpley color. So that's quite colorful as I'm showing it to you. So I've never actually seen this in a pottery thin section. I have seen it in rock thin sections. But if you ever did see this and you think, what on earth is this wacky mineral which is turning blue to purple? One of the things you'd be looking for, of course, would be this. And you can see this purpley mineral has 2 cleavages and 120 degrees. And so if you ever see a mineral with 2 cleavages at 120 degrees like this, and it could be colorless, it could be green, it could be brown, it could be blue, but it's in the amphibole group. That's why quite often I will suggest you identify it as an amphibole rather than hypothesize exactly which amphibole it is. Hornblende, which is probably the most common amphibole, is one of a couple of green pleochroic minerals. So best to just call them amphiboles and explain what is distinguishing about them, and possibly suggest this might be, say, amphibole, hornblende rather, because it's green pleochroic. Talking of which, here we go. Hornblende. In plain polarized light, up this way it's like that, and this way it's like that. So these are oriented in plain polarized light, more or less parallel to, and at right angles, to one of the polarized filter, the one which is polarizing the light. And so you can see orientation to that polarized light is what changes the appearance. So you have green and sort of pale yellowish green, but this is a hornblende. This is a volcanic rock called a tooth. Not tough, a tooth. And here is the amphibole I showed you. A hornblende, probably pleochroic green from pottery, and it's actually from Faza on the west coast of the Yemen. This is basalt here, but let's not worry about that. I've got pleochroism in biotite. Here you can see from the Zabid petrofabric in Yemen. Here's this biotite, which I keep showing you because it's a nice photograph. And when you rotate the stage, it changes color from brown to browner. And there's tourmaline, which is possibly one of the coolest types of absorption, because this is called dichroic quite often. In this case, you could only see 2 going on. It's blue here, and you rotate the stage, and this is it over here, and it's almost colorless. So you can see this bluish change is really quite distinct. And here you can see it in pottery. This is from the western Zagros mountains of western Iran, the Zagros mountains of western Iran, at a site called Sangalan Tepe. And here you can see there are tourmaline. Here is in fact a euhedral inclusion of it. You can see yellowish and bluish are the sort of colors it would have. And here you can see the actual dichroism. You can see here it's like this pale color, here it's a different color, and here it's another color. So that's the this is a muscovite biotite schist. And you can see this muscovite and biotite in the matrix, which you would probably see better if it was in cross-polarized light, but we're actually looking at the pleochroism of this. And here is something I stole from the web, can't remember where, and you can see this tourmaline rotating and turning blue and pink and probably making you feel a bit dizzy, so let's stop looking at it. So next, cleavages. So this has 2 cleavages at 120 degrees. This has 2 cleavages at 90 degrees, as does this. These are both pyroxenes. So it's one of the things that groups the pyroxenes together is high relief and 2 cleavages at 90 degrees. And these are the micas, biotite muscovite, with perfect cleavage, which is starting to sound rather judgmental. But and here we have the feldspars, which all have a good cleavage. And here we have quartz with no cleavage at all, which sounds quite unfortunate, but is actually what makes it distinct. And so quartz is probably quite proud of its lack of cleavage. It's being a very important mineral, and here we have the Silica Tetrahedra, and so it's the structure that creates these cleavages, whether it's along breaks that we can see in these structures or transverse to them. Say if this was a plate in a phyllosilicate type thing, it would have a cleavage at right angles to this view from here. And so it's this structure that creates these cleavages, and they're oriented quite often in relationship to the structure of the crystal itself. So you can imagine something like this might have two cleavages at right angles, and this might have two cleavages at 120 degrees or so. So here's quartz with no cleavage, sitting here without any, and it's got something going on in here. See a bit better here, you can see. And so you look at these and think, is that a cleavage? And of course it isn't. One of the attributes of a cleavage is that they're all parallel. So maybe this might be considered to be parallel to here. But what you should do in that case is look at it in higher magnification to see, does it look like this? And these are fluid inclusions. Fluid inclusions you only get in quartz, and so it's actually diagnostic of quartz. So if you see a line in something you think is quartz, look at it in higher magnification. If it looks like a string of bubbles, which probably would have formed on the surface of a crystal of quartz as it's developing in the melt, that is quartz because it has fluid inclusions. And as I mentioned in an earlier lecture, this is because quartz is the last mineral to form once a melt solidifies, cools and solidifies. And so anything left, like a fluid, would be left within the quartz. So that must be quartz. So here you have a feldspar with a very pronounced cleavage. So this is very easy to distinguish this from that quartz, even though they're both first order gray here in plain polarized light, and they're completely colorless in plain polarized light. But that clear cleavage is going on there makes it quite obvious that this is a feldspar. The cleavages, this is actually a piece of pottery now. This is the stone paste fabric, the medieval, shall we say, an artificial paste, although most of the constituents are in fact natural. So this is mostly made of crushed quartz. And there's a bit of glass. This is actually a fragment of the glass inclusion here. And there will also be clay. And so the recipe for this that we have from contemporary accounts is that it will have about 8 to 10 parts quartz, 1 part of clay, and 1 part of glass. And so the clay keeps it together during forming, and then fuses with the glass to keep the whole body together after firing. And so here it's mostly quartz, but this is a feldspar, probably orthoclase. We'll talk about distinctions between the feldspar when we get to twinning, which is the distinction between them. But one of the interesting things about the feldspars is that because they have a cleavage and quartz doesn't, they will often fracture into blocky shapes. And so if you look at this here, you can see this is probably quartz, not certainly quartz, because this is broken into an angular, shardy type of shape because there's no cleavage in it. It has these conchoidal-like fractures is how it's broken. And so when you see these angular shapes, you're thinking this is something with no cleavage. This is like quartz. Whereas a feldspar will often break into blocky, squarish, orthogonal sort of shapes. And so if you're looking at a piece of pottery and it's mostly filled with things which are first order gray, low relief, colorless and plain polarized light, and you think it's all quartz, what you should do is have a quick look over. Look through as much of the thin section as you possibly can to just look out, is there anything with a blocky shape? And if there is, have a good look at it. Look closely to see if it has cleavages. It may be that it doesn't, and this could be a quartz of crystal, for instance, or it could just accidentally have broken into this. But in fact, this is a feldspar, and that is why it has broken with these shapes. If you look over here, this is another one. Look. So here we have the perfect cleavage of micas. And so you can see it's just completely going cleave crazy here. You can make a sheet of biotite as thin as paper, or thinner, actually. And so it's very easy to cleave, and you can see that this structure is very cleavable and very, very perfect. Here we have a hornblende, and you can see the cleavages here at 120 degrees. And again, we're probably looking down the C-axis to see them this well developed. And here again, this is actinolite, another type of amphibole. And again, if you see something with these two cleavages at 120 degrees, you are looking at an amphibole. And if it's not green pleochroic, it's just another amphibole. So just look up, see which one it is, or just say it's an amphibole that is colorless, or yellowish green, or just green and not pleochroic or something. And so you just describe it. And you have the clinopyroxenes. This is augite or augite. I don't know. I've heard both from people who are qualified geologists. And you can see here in plain polarized light, it's a high relief mineral. And in cross-polarized light, this is actually quite a low birefringence one. This is first order yellow down here, which is within the realm of possibility for pyroxenes. But what is very diagnostic also is two cleavages at 120 degrees. At 90 degrees, okay, don't forget, 90 degrees. 120 degrees is that other mineral. Oh, there you go. Two cleavages at 90 degrees. And here it's a bit less obvious, but basically you're looking at this high relief mineral. You can see it's sort of looking like it's sticking up, with cracks that are more or less going in the same direction. Okay, so this is something you'll see, especially in pottery, where you have smaller inclusions than you might in a rock with bigger inclusions. And so you have this little fragment, and it's high relief. And it may have pleochroism, like this one does. And it will have cracks, which are not awesome, but they are parallel. And you'll have another one more or less at 90 degrees. And so that's how you'll say, that looks like a pyroxene. Here's one actually in a piece of pottery. You can see here cleavages. The one going the other direction isn't very clear, but you're getting there. And so now we come to relief. Like you have the high relief clinopyroxene and low relief phosphates. You have very high relief like epidote, and you have somewhat low relief like quartz and feldspars. So relief is the difference in refractive index between the material and the mounting medium. Okay. And basically means it looks like this. So here are low relief minerals and here are high relief minerals. And it's sort of like a relief map where this is higher than this is. Like this is the valley and this is like hills or mountains, although they're actually all exactly the same altitude. So relief is related to the refractive index of the mineral and how that relates to the refractive index of the medium, like the glue in this case. And so you can actually have negative relief and you can have positive relief, which is problematic to identify in pottery thin sections. But so all that really matters to you is that it has low relief, or moderate high, or very high, even extreme relief. Like if you saw a zircon, you'd say, oh my God, what is that? That has really high relief. And that's how you'd find it. Also, the thing with sphene. So here you have quartz, which is low relief, olivine, which is quite high relief, garnets are high relief, zircon is very high relief. Calcite is crazy. It's sort of like low relief or no relief, and also moderate relief. Here is Enstatite, the orthopyroxene, and you can see high relief mineral. This is sticking up higher than this. Okay, so it's an orthopyroxene, so it's a pyroxene, and there are cleavages. You see, not great, but they're there. Parallel cracks. This one actually looks better. But, so what calcite does, so of course, this range of refractive indices, which is quite high in calcite, creates a big difference or no difference at all with the mounting medium. And so when you're looking at it in plain polarized light and rotating the stage so you're actually perceiving the crystal at different orientations, you will find that an inclusion of calcite may be very high relief or moderately high relief. Then you rotate the stage and it becomes low relief. And here, low relief, high relief. So only the carbonate group will do this. And so you'll actually find even teeny tiny little bits. If you look at it at highest magnification you can, you're not entirely sure what it is, and it changes its relief when you rotate the stage, you're looking at a carbonate. It's very diagnostic. So relief, very important. So you can see calcite, you see, very low relief and moderate relief. Calcite, right there. So then we have types of extinction. The micas have what we call micaceous extinction. Orthopyroxenes have what we call parallel extinction. So here we have biotite, and if you look here, you can, it's sort of like splotchy, you see. And that is this sort of like, it's flickering like stars or something. And this is typical of all of the micas here in cross-polarized light, of course. And in this you can see, so most of this is now extinct, and it's parallel to the crosshairs going this way. But little bits of it are not going extinct. So it has this micaceous extinction, and only the micas do this. So if you can see a mineral doing this weirdness, this has to be a mica. So parallel extinction. So the orthopyroxenes are in the orthorhombic system. And so that means when they are oriented parallel to the crosshairs, they become extinct because they are the orientation of the atoms is parallel to the polarized light. And so here you'd be looking for things like cleavages, you'd be looking for the sides of crystals, anything with a direction, and you're looking to see what happens when it goes extinct. And if it's like these attributes, it could be twinning, it could be cleavages, it could be all sorts of things. And if it's parallel to the crosshairs, here's the crosshairs, then when it goes extinct, then it has parallel extinction. If this was a clinopyroxene, it would be extinct here and not here, you see. So that's one of the differences between the pyroxenes, orthopyroxenes, and clinopyroxenes. Quartz also has a distinctive form of extinction. This is called Undulose extinction. And that's because quartz is one of the only minerals, possibly the only mineral, I think, that can get messed up by metamorphism and start to break up into smaller crystals. And the beginning of this is it starts to stop being in a proper orientation with the rest of itself. So it's sort of like twinning, only it's not. It's just sort of starting to fall apart. Eventually, with further stress, these will form into different crystals of quartz. Like this is a different crystal of quartz here. But right now, it's just forming this undulose extinction. And so what this means is that parts of it will be close to extinct and parts of it won't. So you can have degrees of undulosity, which are described in the handbook. Some will be mostly extinct or mostly not extinct. Some will be entirely extinct in one end and entirely not extinct somewhere else. And so that's more undulose. And so that's described in the manual. So that brings us to twinning, which is the bit in here, which is actually across polarized light, but we're going through this thing to help us. And so twinning is something you find in lots of minerals, but it's very important for the feldspar group. Here, this is a very rare mineral, so I'm not going to talk about it at all. So here we have twinning in calcite, not particularly important. Pyroxenes, again, not very important. You're really looking for cleavages in high relief. But for the feldspars, it is one of the most diagnostic attributes. And here we have Plagioclase with its lamellar twinning. Straight, long blades, lamellae blades of twinning. It looks like a zebra. And the first time you look down a microscope and see an inclusion, it looks like a bit of a zebra, you will say, I found Plagioclase, and you will feel very happy the first time you see it, because it's right there, it's all stripy, and it's Plagioclase, and it's the only thing that looks like that. So that's awesome, isn't it? Of course, here it is in plain polarized light, and you can see it has cleavages. Here we have a piece in a piece of pottery, so you can see that parallel lamellar twinning is diagnostic, even if it's teeny tiny. However, you can see in, look, high relief mineral here, it's probably a pyroxene. However, you could look at this. If you imagine if this was broken down so much, it was this size, you could have a bit in here, and this could be Plagioclase and not be twinned. This is Plagioclase again. This is something we often find in volcanic rocks, and this is zoning. So you can see the twinning going this way and the zoning going that way. You can see it again. Typical Plagioclase. Here is another type of twinning in a potassic feldspar called Microcline. And this is called tartan twinning, because it's sort of crosshatched like this, like tartan, I guess. Very grey tartan. I don't know who would want this as a tartan, but this is tartan twinning. And if you look at a close-up, you can see that this is a very distinctive structure, kind of like a grey tartan. And here you can see it in a piece of pottery. This is a fabric you'll be looking at in one of the labs, the granitic fabric from Belize. And this is Microcline. You can identify the tartan twinning. Here's a bit of tartan twinning in a stone paste. So this is the stone paste from Nishapur, northeast Iran. So it's mostly made of quartz, but there are some feldspars. So here's Microcline. And here, so if you're looking around here, looking at how this breaks, see this is breaking into a sharpy, shardy thing. But this is breaking into a blocky shaped thing. And so this actually has cleavages if you look at it in higher magnification. So that is an untwinned feldspar. So here's an untwinned feldspar. This is the untwinned feldspar, actually, orthoclase. But what, since we're actually looking at teeny tiny things quite often, as I was mentioning with reference to that Plagioclase, what I would suggest you always do is always say, I have X percentage of untwinned feldspar, which for the hell of it I'm calling orthoclase. But basically, this is a feldspar, distinguished from quartz because of its cleavage, which has no twinning. So it's really just an untwinned feldspar, but it's probably orthoclase. So that's probably what this is as well, here in plain polarized light and here in cross-polarized light. This, however, is an intergrowth of a potassic feldspar and plagioclase. It's called Perthite, named after Perth. Here you can see it in higher magnification. You can see you can just see that this has slightly fuzzy, and it can get a bit fuzzy, lamellar twinning. So this is the intergrowth of plagioclase here with this, which has tartan twinning, which is microcline. So you can see how perthite is an intergrowth of these together. And here again you can see the intergrowth of these two feldspars. It's very diagnostic for some petrofabrics from the Yemen, including the Faza petrofabric. And that actually concludes the lecture. So those are the properties. They're in the properties, and you will know the minerals. Thank you.